Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email after the fact. As I think you may know, these Tech Talks have been designed to provide straightforward insights into radio frequency components. We'll discuss the related technology and also the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I'm once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving customer problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objections for the session?
Yeah, thank you, Paul. Happy to. So today we're going to talk about SIM modules. And first thing we'll do, of course, is we'll define what a SIM is, and then why would you want to use a SIM? And there's clearly some good system reasons as to why you'd want to do that. We'll go through the basic circuit configuration, and really what TRM has learned about SIM modules as far as making them successful for our customer. We'll go through some Quantic TRM differentiators, and then we'll wrap it up with a summary.
Well, that sounds good. So to get started, how do we define a SIM?
All right, so a SIM is very often referred to as a calibration injection module or a compensation injection module. So as its name sort of infers, it is a module that is used to allow the system to either self-calibrate itself or allow a point of where you can actually inject a signal to measure to add regular software corrections later on down the system. So SIM modules are a type of antenna feed network. They're typically installed immediately behind the aperture, and the closer to the aperture, the more effective they are at being able to calibrate out various errors in the system, whether it's due to cable phase variations, amplitude variations, drifts over temperature, all those sorts of things. So the closer to the aperture that you can put the SIM, the more effective it is for the system. Backing up just a little bit, it is a type of antenna feed network. Now, if you think about the traditional antenna feed network, they're usually used to steer the beam or something along those lines, where you're manipulating the signal path going to the aperture to be able to go there and affect which direction the antenna is pointing, whether you're looking at having some amplitude or phase control on there to be able to steer the beam, whether you have amplitude control to be able to control side lobes. Those sorts of things are sort of traditionally what you think about for beamforming networks. The SIM module in the purest case is simply a place within that module for you to inject a signal back on those lines that is used for software calibration of the system. It is a hardware piece that needs to be installed in the system to allow that feedback loop to be completed, so that you can go in there and have and allow the system then go ahead and do its self-correction or calibration.
Well, that makes sense. And maybe you could speak a little bit more about some of the reasons for using SIMs. Sure.
Like I said, if you're really looking at what a SIM does, you're looking at it as a point, as a hardware that allows software to do its job. We like to think that you can calibrate most things out using software, using various error correction techniques for phase and amplitude correction. But in order to do that, you have to supply the system with a known good, and the SIM does this. It takes a single known signal, it distributes it out to all of the through lines, injects that signal equally on every through line, and then it allows the system to self-measure itself. Once the system self-measures itself, you can then go in there and then apply the correct mathematical correction that you need in software to be able to correct for any errors that may be inherent in the basically in the rest of the hardware. Things like cable drift over temperature, or even just absolute cable length. Cables are never exactly phase matched. There are environmental changes due to temperature or other environments in the receiver. Essentially, the entire system is self-measured here by injecting a known signal into the very end of the RF chain, and then by measuring that same RF signal distributed across every line, you can actually measure each and every error at whatever frequency that you're working at, and then at that point you can then go in there and apply the correct correction factors to remove it. This is very critical if you're looking at for example, some direction finding systems that are interferometer based, where you're dealing with very critical phase variations between pieces to be able to accurately locate a particular target, or any other thing for that matter. So if you're looking at being able to go in there and actually have some software correction, go in there and make and being able to have a hardware platform to be able to accept that software correction, you really need a SIM.
Okay, so how exactly are these SIMs configured?
Okay, so at a high level, you see the block diagram on the right-hand side of your screen. What you have is you have a common signal that comes in, and that's the calibration input all the way on the far left in the middle. Excuse me, the far right in the middle. That comes in through a signal distribution network or a power divider network. It is then fed into the coupled port of a directional coupler, which then takes that energy and then injects that signal back onto the through lines, back out the outputs in order for the receiver to be able to receive that signal. The nice thing about this sort of network is that everything is phase and amplitude matched going through the system, and therefore a single known signal that is put into the calibration input can then be measured on every output. And basically, since we have a directional coupler feeding it onto the main line, the signal that is put in from the calibration input is naturally isolated from the apertures. Therefore, the aperture does not radiate while this injection signal is being put into the system. So it becomes a very convenient way to go in there and be able to inject a known signal back onto your signal lines to have the system be able to measure that. And like I said, it's a fairly straightforward block diagram. The devil's in the details as far as how we actually manufacture this, and that's kind of where we're going next.
Yeah, and I've also heard you say that some of the design steps when using SIMs are highly critical, and I wondered if you could explain which ones and why.
Sure. So really, what's really important here is that to understand is that any error that we're going to see in the SIM will not be removed from the calibration routine. The whatever residual error is in the SIM will be baked in, so to speak, of the overall system calibration. So the SIM itself needs to be as good as it possibly can be. So therefore, what we're really concerned with is phase and amplitude match through that entire power divider and coupler network across all the ports. We're also very interested in making sure that we design a part that is extremely stable over temperature, vibration, and all the other environments. Since this is the one component that is going to be adjusting for all those variables, it really can't vary across those same variables, otherwise it won't do its job. So it's very important that we have a very solid, steadily stable and repeatable unit that is stable over all of its environments, and that is in and of itself a high-performing unit with very good phase tracking and amplitude tracking in order for it to be able to do its job. I will say that TRM has great experience in building these. We have built these components that work over a wide variety of environments, and we have some really good designs in place that mechanically really result in a very stable unit. coming through with how these things are built. So it's really an exciting process that we have here at Quantic TRM in designing and building these components, so that we do have a very good stable design with good heritage in building these components.
Well, excellent. And certainly I'd like to hear a little bit more about some of the differentiators that Quantic TRM does bring to the table here. But before so, maybe you could summarize this presentation a little bit.
Sure, absolutely. So really, to summarize, a SIM is a type of antenna feed network. It is a part of a system that provides an injection point for a known signal to get put back onto the receive lines, so that you can correct for any kind of system inaccuracies going through there. It is critical that the SIM, being the injection point, and since it is a point that is not calibrated out in this process, that it be as accurately as possible. And in knowing that, I think it's very important to understand that the stability of this part is critical in having it work over the full environment. And Quantic TRM has been building these parts for decades, so we really understand a lot of the subtleties going on with these sorts of designs, both mechanically and electrically, to end up with a very good, stable unit.
Okay, thank you. And maybe now you could talk a little bit more about some of the differentiators that Quantic TRM does bring to the table in this area.
Sure. What I'll say is the biggest differentiator with Quantic TRM is we like to work with our customers. We like to go in there, have the discussion, and find out really what it is that you're trying to accomplish with your particular program and system, and work with you to make sure that the component that you get will indeed function and give you the functionality that you need. That is I want to say that one of the biggest differentiators that we have is we really enjoy going in and working with our customers to make sure that the component that they get is really the best component for the system. We want our customers to be successful. We go through, and as part of that, we make sure that we build the best component possible with careful materials and design choices. I will say that we pride ourselves on mechanical packaging as far as building things that are robust, stable across a wide variety of environments. We also supply objective evidence for performance across those environments, which is very often something that many of our customers require, and we're very happy to provide it. And I always like to say that Quantic TRM is a solution provider, not necessarily just a component provider. So we're happy to support our customers. We like working with our customers, and we like speaking with them to find out really what it is that they need to do, and work with them to make sure that they get the best product possible.
Excellent. Well, thank you for that. And we do have, well, I think we have time at least for one question. And one of them is that as follows: can the functionality of a SIM module be incorporated into a more standard antenna beamformer?
The answer is absolutely yes. Depending on the nature of the beamformer, many beamformers are quite complex. A SIM module could be incorporated in there, either on the output of the network or right at the aperture. It can really go in either place, whether it's on right at the aperture, in which case you would be able to calibrate the beamformer out at that point, or whether you want to put it post beamformer and put it there. So either place. Remember, the whole function of a SIM is to be able to take a common signal and eject it back onto lines back on those connections, so back to the avionics, so you can actually go in there and remove any system errors. At any point in the system where you want to have that functionality of having a known signal and inserting it back onto some lines so you can measure it, can be a point to include a SIM. It is not just a SIM only module. It could be incorporated certainly into another beamformer, or quite frankly, any other place in the system where you need that sort of feedback loop, or a hardware injection point to have this correction where you can then apply in software.
Okay, well, thank you again, Shaun. And thanks again to all of you for joining us. In conclusion, I think the bullets on the screen say it all. And going forward, if you are a customer and have more questions, or if you'd like to discuss details with one of our engineers, we'd love to hear from you. Please feel free to call our engineering hotline. The number is on your screen, 888-677-6877. And there's no cost for these calls. If you're one of our field sales representatives, then you know your calls are always welcome. And you can also submit questions directly through the sales rep portal on our website. In case it's helpful, our next Tech Talk is scheduled for Tuesday, May 23rd at 1 p.m. Eastern, and the topic will be high-frequency solutions. Thank you all once again, and thank you, Shaun.
Yeah, thank you.